All right. I think this is on. Yep. We'll go ahead and get started for the M-Cubed seminar. I'm pleased to welcome Morris Weisman. He's Senior Scientist Emeritus in M-Cubed. He received his bachelor's from Worcester Polytechnic and his MS and PhD at Penn State. He came to NCAR in 1979 in the previous mesoscale prediction section of M-Cubed. He became a senior scientist in 2004, and at the end of 2024, transferred to emeritus. Morris is well known for his work on convective weather and forecasting high impact weather using convection allowing models. Has been lead PI in several field campaigns. He's a fellow of the American Meteorological Society. And of course, he's the progenitor of the MoCast, which a lot of are familiar with. And I just asked him if that's going to continue, and he said, hopefully, especially for particularly severe events. So, welcome.
Oh, it's great to see everybody. I mean, 45 years goes really, really quickly. And now I'm beginning to recognize, how bad it really was for all the different people and all of the different groups that I got to work with. Field campaigns, a lot of field. Jim Wilson's here, that's great.
I beat you by 2 years.
Anyway, the idea of doing this was that it just seemed like when it came to convective research, an awful lot's happened in 45 years. It's rather amazing. It's sort of summarized, at least from the numerical research perspective, by the changes here. The Klempner-Hansen results from 1978, 36 by 36 by 10 kilometer domain. It took a couple of days to run, I think. And you had to bring a deck of cards up to a desk and then come back the next day for output and whatever. And now we have MPEX, doing the same, almost the same resolution globally. What I'm going to talk about today, really is just a part of a much larger community effort over the last 45 years in terms of the observation, modeling, and research on convective storms. I couldn't talk about everything. That would take too long. As it is, this talk is going to last at least 3 hours. Feel free to leave after 2 if you have something more important to do. But I'm limiting it mostly to the core things that I did it with M-Cubed and with EOL and field campaigns and some of the educational stuff. Hopefully giving you a picture of at least the kind of career that NCAR used to be able to support. And we'll see if the future allows that. But that's another thing. That's the last I'm going to talk about that. Gretchen's getting upset. No, anyway. So let's get started and go back to 1979. And you can see what NCAR does to somebody.
Did you hurt him?
I still have that T-shirt, by the way.
Which arm?
But anyway, I came out of Penn State just having my master's degree, and I had no idea what I was getting into coming out to Colorado. And I'm introduced to this group of people. Joe Klemp was the person who hired me. Who's that person next to Joe up there? Do you know who that is?
Joe's brother.
No. Rich Rotuno, who had arrived at about the same time. He's standing there by the ward, tornado chamber. Doug Lilly was the leader of the group, I think, back then. Some other notable people at the time, a young Don Lenschow, who's still, is Don here? Yes. Yeah. You haven't aged a day. Peggy Lamone, of course, who Yay, yay, yay. John Wingard, who was the head of our group for a while, then went off to universities, and a whole bunch of other people. But walking into a group like this as, just coming out of a master's degree in college was really quite difficult, let's say, emotionally. I thought I was going to take a job with somebody with, a professor with gray hair or something when I heard I was getting a job with Joe Klemp. And here he is, a hippie, So anyway, I was hired on to work with the reasonably new Klemp-Wilhelmsen model. There's Joe and Bob Wilhelmsen in Florida, I believe, a few years ago. A very, very simple cloud model. There were other similar cloud models coming out, like from Bob Schlesinger and others up in the CSU. Bill Conton, I think, was working in the same range. But very, very simple models, very, very, just basic equations. Since it wasn't trying to forecast whether just, do the research, horizontally homogeneous conditions, you didn't have all the issues with real-time forecasting with it. One of the interesting aspects of it, which we'll keep coming back to, is how simple the cloud part of the model was. In particular, it was about 20 lines of code. And there was about 1,800 other lines of code that went around the cloud. And that's all that was in there. And it's amazing to me how much it was able to reproduce with just simple conditions. I mean, nowadays, this is what the cloud, like Hugh Morrison and whatever. I mean, whatever. Yeah. Some of the early research concentrated on, the most intense of convective storms, supercells, because they were isolated and they certainly had a lot of impact on things. But certainly tornadoes was one of them. So that was one of the, the early efforts was to simulate these long-lived storms that produce tornadoes. One of the early things that people noticed was often these storms come from splitting cells, the right mover being a cyclonic rotating storm, the left mover an anticyclonic, and that was always kind of mysterious. And in the early, even back in 1978, it was one of the easily reproduced features of convective storms that if the shear was strong enough, and it was a unidirectional straight shear profile, you got basically splitting storms if there was enough instability and whatever. In this particular case, the Coriolis force was included, and so the right mover is a little stronger than the left mover, so it's not symmetric, but very often the symmetric aspects went on. Another one of the early efforts, because of the on-site use of Doppler radar, you could actually begin to compare the modeling results to the actual observations. And the May 20, 1977 Del City storm, Klemp-Wilhelmsen and Ray, 1981, presented it, and it became the object of almost all the cloud modelers out there trying to reproduce this because they had very, very good observations of these storms, and we could compare it to the Doppler radar. And so on the top, the radar observations, and on the bottom, the Klemp-Wilhelmsen Ray simulations, at various levels in the storm. And, wow, a simple model with, simple microphysics went a long way to replicating the observations. And that was a real positive insight. This was a real interesting case. Wilhelmsen Klemp 81. Storm develops down here, splits, multiple splits, and you get this very complicated pattern from one cell out a couple of hours later. You start with a single bubble in the model, it splits, you get multiple splits, and it says, whoa, this is going to be easy. Well, it was advantageous that this worked like this. But again, it showed that these simple models had the ability to represent a lot of the phenomenology of these kinds of systems. And because you had the cloud model, you could go through and analyze why it was happening. For splitting storms, you're tilting vortex lines up, producing cyclonic and anticyclonic peer at mid-levels, which was associated with low pressure, and enhanced updraft under those. If the hodograph was a straight hodograph, it just did this symmetrically, and you got the splitting as the forcing on the flank of the storm spread apart. That was a real breakthrough, I think, in our understanding of supercell storms. And then, like I said, with a straight hodograph, one cell, they move off, but they're identical mirror image storms. If you add curvature to the hodograph, like the curve there, the right mover becomes one of the classic looking supercells that you see, from, on the May 20 case and a lot of, tornadic storms. So, again, very, very simple model, able to reproduce what seemed to be very complicated phenomena. Then we got into more of the details of the supercell analysis, showing how the horizontal vortex lines in the cold pool contribute to low-level rotation and tornadoes within the storm, and perhaps that. Rich Ratuno, of course, got involved with all of this. Rich is somebody you go into his office and you're never quite sure what's going to come up. But it's going to be interesting. Going on, of course, Rich is worldwide known as one of the best dynamicists when it comes to tornado processes and whatever. But I knew him more as the philosopher. But I did learn an awful lot from Rich over the 45 years. What was I doing while all this was going on? Besides causing trouble, I was looking more at the environments of these various storms, looking at the relationship to vertical wind shear, which is one of the contributors to allowing the storm to develop rotation, and CAPE, buoyancy. This Weisman clump sounding, Joe is really the one who produced it, but I used it. And I would have, it would have saved me a lot of trouble if it was the clump Weisman sounding. But that became, it tended to work really, really well. And the reason is because it was produced, and it doesn't look like any sounding in the real world. It was very, very moist. But I'll tell you, for about 30 years, this is the sounding that researchers at universities first use to try to simulate convective storms. It works really well because mostly, I think, it's because it's very, very moist, and which makes it easy for the storm to develop their own dynamics. And you can see as you go through the shear regime, ordinary cells, weak shear, more multicellular activity, and eventually getting up to the full-fledged supercell as you increase and change the shear profiles with these kinds of systems. It also presented this in a paper in 1982, where we looked at the, over the Cape range over here and the shear range down here, splitting into the initial storm maximum vertical velocity. And you can see the strongest initial storms are with very weak shear, and they weaken down as the shear gets very, very strong, the negative impact of shear on the storms. There's a little bit more evolution beyond the initial cell with a little moderate shear, but the split storms and the supercells are in a very, very well-defined high shear regime. And that has held quite well over the years. After dealing with more isolated cells and the computer power getting a little bit stronger, we began to look at convective systems. We started with the 2D squall line because 2D gives you some freedom in terms of the domain size. with the computer resources. And later on, the more complicated Boeco type of configurations. And this is just an example of a squall line type derecho system. These are the things that can produce, hurricane type winds over 50-mile ranges, if even longer. We started working on this based on some results by Alan Thorpe back in 1982, who varied the shear between the surface and 2.5, kept that constant, and changed the shear profile such. And what they found was that the best result occurred when you had just all the shear, or limited to the low levels, and that was this case right here. And that was the steadiest storm. That was the beginning of the concepts of RKW theory, a theory for strong, long-lived squall lines. Let me note that there's a very, very important lesson here. The title A theory is very, very different from a title with the theory. And we've dealt with that we are still dealing with that today. But Rich and Joe and I came up with really important analyses. The whole idea is based on the fact that the density current interacts with the shear in the environment. And so you can measure the strength of the density current by C, the theoretical speed of propagation. And the shading here is the cold pool. And what we found was when the shear was weak, so that C over delta U, the delta U being the magnitude of the shear, was greater than 1, you got an up shear tilted system. When C over delta U was about 1, there was a balance between the circulation generated by the gust front and the circulation associated with the shear, and you got much deeper and more erect vertical motion at the leading edge. If the shear was too strong compared to the gust front, then it tilts over. And so that suggested an optimal state. That was another word that we had trouble with. In what way was it optimal? And again, over the 40 years, we're still trying to explain that. Anyway, and this was applied to full-fledged squall lines, where the convection was represented by horizontal vorticity. If there was no shear, it was symmetric. You added the cold pool, it tilts it over. If there's no cold pool and this shear is stronger than what was here, then it tilts that way. And then you can come up with a balance. It also helps you explain the evolutionary stages of a squall line, in that initially there's no cold pool, and so it will tend to shift, tilt down shear. As the cold pool develops, it becomes more upright. And then eventually, most cases, the cold pool gets strong enough to produce this rearward evolution. That develops a rear inflow jet, which is an important component of the squall line as well. And again, the question of optimality really relates to what metrics you're using for optimality. If you just use the lifting at the leading edge, then the RKW optimality works. But if you look at things like the total rainfall that was produced, the amount of wind that was produced, there's a far wider range, and there are a lot of other things that are contributing to that. But we stand by RKW theory. Once we got past that, we began to be able to look at these more 3D squall lines, Boeco type of features, where you get this very, very bow-shaped system, but you also get these circulations associated with the system that can enhance it. In particular, you tend to get a large-scale acyclonic circulation at the southern end of a limited system and a cyclonic circulation at the northern edge. And that enhances the rear inflow jet. And of course, none of these features are in the 2D theory. But again, if you start with the line of cells, what we found is if we let it evolve with time, Acyclonic circulation at the southern end, cyclonic at the northern end, rare and flow jet. This particular simulation did not have Coriolis. You add Coriolis, and you get a dominant cyclonic circulation at the northern end, just like you tend to see. And then you also get a lot more of these features along the line, which are really significant for producing tornadoes. In the early 90s, COMET came along to help train and upgrade weather forecasters, and I was luckily part of this with their COMAP courses, training the Weather Service SUD, and also producing these training modules online. And they did amazing things with the results of Joe Klemp and Rich and whatever, and producing these kinds of plots and schematics and animating them. Unfortunately, I couldn't get the animation to work for today. But all of those results from about 1979 to about 1990 showed up in these COMET modules, and the whole Weather Service was basically introduced to these kinds of results from numerical modeling results. One of the star attractions was something called the convective storm matrix, which allowed you to go through different holograph shapes and magnitudes of CAPE, the Weisman Klemp sounding again, and various shear magnitudes. And it would actually run a simulation for you. And these were different kinds of simulations, extending from those classic supercell to a bow echo developing with circulation and so forth. And basically it showed, it allowed the Weather Service people and people at the universities to learn within 4 hours what it took about 10 years for us to produce between 1979. They could see the same relationships and so forth. It was just there, and available. I think it's still up, and I think it still runs. Is that, Russ says it's still running. And there was a similar system for convective systems as well that showed simulations. Nowadays, people who can just run something like George Bryan's CM1 on their phone, and you can get the results in a few minutes. And so, it is different. But back then, it was limited what you could, do on the run. During this period, we also had a lot of postdocs who were coming in and were excited about working with these new numerical models. Jeff Trapp was one of these people, and he worked on these mesovortices developed along the leading lines of squall lines and whatever, and that's become a very popular topic now, in terms, especially in the Southeast, where they have a lot of tornadoes and squall lines and whatever. And Howie Bluestein, would show up, and occasionally he would come to the office when he wasn't chasing or hiking, looking at how storms interacted along lines. And so from 70 minutes to 85 minutes, these are vertical cross sections as two storms are colliding together, and you actually see how the updrafts interact with each other, and the rotation develops or doesn't develop. And there were a whole host of different environments that we did that in. George Bryan shows up around then, and well, he thought that his model was much better than everybody else. But, he's of course pushing the frontier. This is our 1 kilometer squall line. He said, oh no, you need to go to 125 meters, which is a factor of about 64 more expensive. More than that, actually, I think. But in terms of the dynamics, really getting the details of the updraft and the mixing and so forth correct, obviously, it does improve things, but it makes it a lot more expensive. So you can't do that real time. Maybe in about 10 years, we'll be able to do that. And Bill McCall, who unfortunately we lost about a month ago, very, very sad. He introduced us to the idea that in these hurricane rain bands, you've got tornadoes along these outer bands, and that the tornadoes were associated with little supercell storms. Almost no buoyant energy, but very, very strong shear. And he showed that you could actually get long-lived cells that could be very, very shallow, but had the same dynamics and structure that could produce tornadoes. This has also become very popular with a lot of the field campaigns in the Southeast now. People, Stan Trier has actually done some work on that with Stan. Stan, hi. Hi, Stan. Yeah. Whatever. I forgot to mention back, no, I guess it's later. Never mind. A big component of this was field campaigns. And I can't say enough about the value of getting out and actually looking at the real weather, even just staring out the window. The whole idea of the MOCAS was to get people to steer out the window at interesting things that were happening. But the field campaigns really allowed some real valuable interactions with the community. It allowed you to really validate the numerical models, comparing them to the radar and so forth, collaborate with the community, and I'll tell you, sampling the small town fine cuisine in this country is a must. That's all I can say. You can't beat the chicken fried steak at the Lyman truck stop, and that's all I can say. You have to try that. But I was involved in, about 7 different programs in the 80s. Jaws and Cindy. Jim Wilson had left. He had a phone call, I guess. And that was looking at, downbursts and microbursts and whatever in eastern Colorado, and Ted Fujita, generated the idea of the microbursts out of that. I was involved in Vortex 1994, 1995, traveling around the West and eating at such places. It took a couple of years to recover from that. And I'll talk a little bit about these 4 cases, the first being stepped 2000, the Severe Thunderstorm Electrification and Precipitation Study. It was situated in Goodland, Kansas. And the idea was to get observations through these storms that would show the electrification processes as well as the precipitation processes. And it was really quite a collection of researchers that I hadn't been involved in before. People like Charlie Knight, I was there, Eric Rasmussen, Steve Rutledge, Jay Miller was a very, very important part of that program as well. But we had to stay out in Goodland for about a month. We had this one tornadic supercell that we got to take observations in. What I was interested in was the difference in precipitation types between what you call classic supercells, where the updraft's on the southern flank and the rain is on the northern flank or northeast flank. And this phenomena that seems to occur, especially near the dry line, of these storms that seem to produce the same basic updraft structure, but no rain. And it's still kind of a mystery. We did get some storms like that during STEP. Here's an example of one. And you can see that, around the updraft, there's no rain. The rain is much further off. So how is it producing so much, anvil and whatever, and not having anything fall to the ground? We were going to observe that with the T-28. Here are some of the electricity balloon people launching into that storm. Yeah, it's sort of sad about the T-28 because it was flying in that tornadic supercell in Goodland, and it ingested too much hail and precipitation into the engines, and the engines quit. And they had to glide back to the Goodland airport. And that was the end of the T-28. Is that right, Jim? You can confirm that story. So that's why we've been struggling to perhaps get an in-cloud plane since. It's always interesting dealing with the local population on these field campaigns. That's Dave Russ trying to explain to this local sheriff why we were disrupting his town. I also learned the very, very important first lesson in diversity. I'm staying in Goodland, Kansas. We used to live eat at a restaurant a couple of times a week, a big circle of about 8 people. People from NSF would come in and whatever. And so towards the end of the experiment, they came up to this table, the waitress, and she came over to me, and she asked, "Sir, we've been wondering all this time, what are you?" This is very true. It tells you about the different experiences you get with these kinds of events. Shortly thereafter, 2003, the BOECHO and MCV experiment in just east of St. Louis, Mid-America Airport. This was probably the biggest field campaign that I was involved with. Chris Davis was one of the chief PIs for that as well. And there were 2 goals, one to study with 2 airplanes, the NCAR airplane and then the NOAA airplane, producing quad Doppler analyses, and also to look at these BOECHO type configurations that developed and produced severe weather. The other aspect of it was that these kinds of convective systems in some environments produced big vortices. What's great about these experiments, the fact that you get to collaborate with people you wouldn't normally, weather service people, people from the university, other labs and whatever, and everybody gets together and talks through the day observations and what we're anticipating doing. I'm trying to explain to them, what we're looking for. It took a while to explain that. No, but we did get some good bow-shaped systems during this, and Roger Wakamoto is among some of the people who have gotten some really good papers out of the development of strong winds with these types of systems. Chris Davis and Stan Trier were more interested in these mesoscale convective vortices that show up the next morning after one of these big convective systems decay away. And they produced really an annoying number of papers on this. But really, actually, they put the topic to rest. We now know what we need to know and how that they tend to trigger new convective systems during the day and whatever. What was particularly rare about BAMEX is we got hit by the event we were looking for right at Mid-America Airport. We got one of these intense BOECHOs here on 10th June 2003, and it turned out to have a tornado and very, very strong straight-line winds right on top of the Mid-America Airport. And while we were watching the storm come in, a security guard ran up to us and claimed we had to, take shelter down in the basement. And so everybody went down into the basement. And the security guard there is trying to explain to Lance that there's a storm out there that... Lance took it very, very well. But he was just concerned with our safety, right? Yeah. And this is what it looked like outside of Mid-America Airport afterwards. The power was out in the whole county, and we had to within about 2 hours, Jim Moore and people got us reestablished at a motel somewhere. And up and running within a few hours. But, Jim Morris said he had never been in an experiment with, that got hit by what they was trying to study. So that was very, very special. Another interesting thing happened during the BAMEX field campaign, and going back a little in history, Doug Lilly was one of the leaders of our group over the years, and as the models and computers were getting better and better, he began to recognize that predicting convective storms should be possible, and we should spend time trying to do that. He also noted that the task is not trivial, as we all know. But between about 1996 and 2003, people started doing that, not in real time, but after the fact, doing real convective weather with stupid models like MM5 and whatever. And CAPS had another stupid model and whatever. But in 2003, the WRF model arrived, and which was so much better than everything else in the world. But the real interesting or the positive thing about it, it was built with the intention of simulating high-resolution phenomena like convection. And gust fronts, supercells, mountain waves, hurricanes, and even PBL turbulence. And so it made it to be a very, very good model to apply towards trying to, in real time, to forecast convection. And so during BAMEX, we decided to try to run a 4-kilometer version of WRF during the experiment and use that those simulations to guide the operations the next day, about like a 24-hour forecast. This was basically done almost entirely by Wei Wang, who we couldn't have done this without. And every time we ran it, we got results like this. Here are the observations of that June 10th Bow Echo, and here's the forecast. Gee, it's easy. Well, that was, I think, the only case that actually worked. But it made it that it was possible. And so for several years, people started doing this in real time. The Weather Service picked up on this and started incorporating real-time, high-resolution forecasts into the hazardous weather testbed spring forecast experiment. And people from all over the country, you see, oh, gee, there's, we know this guy, and Glenn Romine, and who else is here? Oh, Ryan Sobash is there from back then, and working with NSSL in this program was really incredibly positive in terms of the interaction between the applied weather forecasters and the researchers, getting feedback and going back and forth on what was working and what wasn't working. The other thing that happened during this time period, again, I'm going to show you a good case, the second good case we've had in 20 years, was that we found that the WRF model at about 3-kilometer resolution could produce things we've never seen before. And it produced things that we hadn't seen in the nature before. Here is a case of a bow echo that went through Missouri and produced like an eye, a hurricane-type eye here with hurricane force winds on the back side of the system, almost no forcing aloft. Here is the circulation here. Now, I had never seen anything like that in my weather watching days. Nobody else I knew of had either. Here was our 24-hour forecast of this event, right here. Working on this with Clark Evans and Lance Bozart. And if you look at the structure of this feature up here, we reproduced this meso-low, about 8 millibar meso-low, 60-knot steady winds on the backside, reflectivity producing an eye with the isotopes descending down. These models are able to produce things that we didn't envision happening. And we've seen that several times. And when it comes down to could AI do this? Well, if AI doesn't have an example like this from the past, how is it going to know that it's going to produce this? But a real model, dynamic model, still can produce things that we don't anticipate. Tom Galano worked on this again, another postdoc. He's down in Oklahoma now. And this is something that the community perhaps doesn't agree with me on, but it seems like the evolution that we saw from that super derecho is an awful lot like the warm seclusion process of synoptic scale cyclones. And Tom looked at that and tried to explain what was different about that and whatever. The paper's been out for 5 years. I think we've gotten 3 citations. But I am hopeful that it will move forward. Another exciting aspect to this was getting together with Lance and having a NCAR colloquium back in 2006. Here are some of the people who are in this audience now. Clark Evans is there, Dan Dawson there, Adam Clark from NSSL, Brian Tang, Dave Dowell, oh, there I am, Howie Bluestein, Lance, Tom Galano. Oh, Clark, you're the tallest one there, as you usually are. But this was an amazing opportunity and collaboration, and ever since the colloquium, a lot of these people are still working together and communicating, and that's the value of the kinds of things a national center can do beyond other people. I even went and interacted with chemists back in 2012. This was very strange for me because I had no respect for chemists. I had heard that there was a whole building of them. But Mary Barth convinced me to get involved, and it was really, they're really nice people. And again, we used the model to help forecast events and used the cloud model, the WRF model, to actually simulate the track of tracers from the convection, which is what they were interested in, where the chemistry was going and what was being lifted up from the boundary layer to the top of the atmosphere. So that was a great interaction as well. During that was another one of these significant isolated events. The morning of 29th of June, the model produced this, and we discussed this during the weather briefing. It had nothing to do with DC3 per se, but I made a comment saying, oh, this is going to be great for funding because it's headed right towards Washington. And I didn't think it was really going to happen, and there it is, then it happened. And it's still considered one of the biggest derecho type events in recent history in terms of the impacts. There's the SPC storm reports on the left and the 3-kilometer WRF forecast wind speeds. And again, we don't get a forecast this good all the time, but again, I had never seen a forecast as strong as the one that was produced here. I didn't believe it was going to happen, but it happened. The model was able to do that and to give forecast guidance. More recently, now we're moving with computer resources to ensemble representations of all of these. Craig Schwartz, Ryan Sobash, Glenn Romine, Katie Faso, and I were working for 3 years. The NCAR WRF Ensemble was available on the website, and forecasters just loved it. I think it proved to NSF once and for all that high-resolution forecasting was helpful, and that ensembles could really offer a lot of useful information to the forecast process. You can see the abstract from the BAMEX article. NCAR's real-time convective allowing ensemble began as an experimental forecast demonstration to advance research in high-resolution ensemble design and evolved into a considerable outreach effort unifying research and operational meteorologists. This is the model of what I think NCAR is supposed to be. and they brought it together for this and guided the whole field on the direction. Others were, doing ensembles as well. Ours were just better, But it's a 10-member ensemble. Here's one event, a derecho that went through the central U.S. and all the different model members. They were all a little different. Some got it, some didn't, but they all represented the possibility of a strong event, which was a lot more information than we would get just from a very coarse resolution simulation. And we're moving ahead with that. The mesoscale predictability experiment. This was done back in 2013. We had found that when these real-time forecasts, that they were most sensitive to the initiation state that we put in the model. And if the initiation state was off a bit, we could get huge errors as opposed to just small errors associated with microphysics or whatever. And so we went out and tried to use dropsons ahead of convective systems in the tornado belt, Texas, Oklahoma, Kansas, Nebraska, and get enhanced observations in the morning around 6 a.m. to enhance the initial state of the atmosphere. Here's an example of our day on 31st May, the day of the El Reno tornado. Here is the early morning flights and the circulation that was developed. Here are the storms that developed during the afternoon. And again, the ensemble wasn't perfect, but again, it had some aspects of the event. And this is what happened on that particular day, one of the largest and strongest tornadoes in history on that particular day. And we have lots of observations and model simulations to study these types of events. And now we switch to MPAS. The latest and greatest. MPAS ensemble now is running as an ensemble, just like we did with WRF. Here's an event that occurred just a week ago that killed 28 people in Kentucky and Tennessee and whatever. And on the top, you can see the evolution from isolated supercells to a line. And here are 6 of the 8 forecasts from MPAS, which again showing the intensity of convection in that area, showing that there's some value to this. So MPAS, it's doing as well as WRF, it seems, right now, and that's a positive. And now Craig is running 3-kilometer global MPAS. For the first time this year, it's available online. And this is the first time we've done that. And looking at the ability to simulate convection and other features in very, very different environments, tropics and mid-latitudes, the Antarctic and Antarctic. And this is like the 6-day precipitation total showing the ITCZ there. And here's their forecast of the severe weather event in Kentucky. So we've come a long way in 45 years, from the little splitting cell to a global, high-resolution convective resolving simulations. We've learned a lot. There's a lot more to learn. I want to just come back and again give my thanks to all the people I worked closely with over 45 years, the community. This is what happens at a national center that can't happen perhaps at a single university. I'd like to thank everybody, but the reality is, if I did anything wrong over 45 years, it was their fault. They misguided me, and I'm not going to take responsibility for anything. And we'll just stop here with a nice sunset view. Maybe is this one of the last sunset views of NCAR we might have? Who knows? We won't get into that, but it's my sunset in terms of my jobs here. Thank you.
All right. Time for questions? pretty sure someone wants to ask something. All right.
Yes. Or correct me for, Yeah, feel free to correct me if I got the history wrong.
I wouldn't dream of doing that. No, my question is about what the next, say, frontier of convective forecasting is in your view.
I think it's the tropics. All of these results, seem to be based most on very strongly forced mid-latitude convection, and the tropics have much weaker amounts of buoyant energy available to them. Unfortunately, that means you need higher resolution to simulate them properly. And we're only now just getting to the point where we can run high enough resolutions in the tropics to do the same kind of analyses that we've done at mid-latitudes. We've gotten away with 2, 3, 4 kilometers at mid-latitudes. But even back in the early 80s, we tried to do tropical convection and failed miserably because there was too much mixing. The Cape wasn't high enough. And we found that we had to get down to like 500-meter resolution in very small domains to get anything that looked like a tropical convective system. Nowadays, we're finally beginning to get down to 3 kilometers globally, maybe with windows down to 1 kilometer. But we're still going to have to get down to, I think, less than 500 meters to get the same kind of physical understanding from the simulations for the tropics. But that's wide open.
Morris, I didn't realize we had to throw the microphone. 'Cause now I know what I'm going to do with it when I'm done. Anyway, thank you, Morris. Excellent. And we shared a lot of good times together and sometimes interesting times in these field projects. My question to you is related to what Chris asked. What field project would you do, given unlimited resources, to answer some of your questions still remaining in your line of work?
Ooh, that's a good one. I don't know. I think there's still, for mid-latitude severe convection, I still think there's an opportunity to get better initial states in the simulations. That was one of the strongest signals we've seen for the last 10 years in these real-time forecasts is, very often, things are a little off from the different ensemble members, but there are times when the entire ensemble is off, which tells you something's really missing. And when we've looked at those few cases we had time to look at, it seemed like the sensitivity could be explained by changing the initial state, using the NAM initial conditions versus the GFS initial conditions, European initial conditions, or whatever. One of the real sensitive parameters, most sensitive parameters for convection, I think, is mid-level moisture. The reason, and that even goes back to the Weisman-Clem sounding, the reason it worked so well is it had very, very deep moisture. We didn't worry about mixing in dry air and so forth, and it was easier to get convection to go. In EOL, I think you've been working on LIDAR to get good observations of moisture up to mid-levels. And getting a field experiment that better defines that environment up through like 700, 600 millibars, especially moisture-wise, could still make a real significant impact.
Is your friend Rich? Is a note from Rich.
Uh-oh.
It's not a question. Greetings from Taos. Thanks for your contribution to my siesta.
Yeah,
Congratulations.
Yeah.
All right. Are there any other questions? Okay.
Thank you. It was a great presentation. For someone who just started NCAR career, it's very inspiring to see how far a scientist at NCAR can go just after a master's. So I'll go with the tropical theme here. So we see that most of our global and regional models really suck over the tropics. And being involved in a project with Singapore, we're seeing that on the first hand. So my question to you would be, where would you like to invest your most amount of consideration and energy to improve the model? Would it be microphysics, cumulus, or something else?
You can get rid of the complicated microphysics. We showed that. You didn't need no, that's not true. I think the simulation resolution. I think we learned a lot about mid-latitude convection in the 1 to 2 to 3 kilometer range. But I think to learn the same level of understanding about tropical convection, you need to get down in the 100 meter to 500 meter range for resolution to get because all the forcing is a lot weaker, and so you need the higher resolution to represent that a little better, I think. So that would be my suggestion, is to get numerical resolutions down, way down. And then we'll see what happens, but yeah.
Oh, a couple more questions over here.
Morris, that was terrific.
Thank you, Peggy.
And I'm going to make a plug for GATE. That sounds kind of weird because it happened 50 years ago. But one of the things we discovered from GATE is that the updrafts in storms were surprisingly small in diameter, which supports your idea that the resolution has to be a lot better to resolve these little guys. And it leads to different dynamics at the leading edge and so on that are quite interesting and quite different. But I think there also is a possibility for large squall lines. They do happen in the tropics as well. But you got a lot of these little dinky things that probably bore you to tears, but they have similar, they have similar properties in some ways to squall lines.
Thank you. Yes, I agree. Yes.
Thank you, Morris. So you alluded to some of the controversy around RKW theory and other harebrained ideas.
Any other questions?
Other harebrained ideas you put out there over the 45 years. What do you see as the biggest controversial or challenging problem for severe convective storms research and operations right now? And what do you think it's going to take to address that?
I think right now our understanding of convection is way up there right now. The high resolution real-time forecasts, we still have work to do on that. But you can't help but notice that in all these recent, big hazardous weather outbreaks, that the forecasts were great, guided by high resolution and everything we know about convection and whatever. The guidance was really good, sometimes a day or two, sometimes even 3 days ahead. But society doesn't really know how to respond to that information. I think that's where the big gap is right now.
Thanks, Morris.
Let's take one more question from Peter.
Nice talk, Morris. What role do you think AI will play in this particular field?
We have a long way to go before we know, I'd say. For convective scale forecasting or whatever, it's not clear that the current attempts at AI really address the kinds of very severe, intense, small-scale features that develop within these kinds of convective systems, within these kind of weather systems. Where AI seems to have shown skill is out at 15 days, where, the 500 millibar anomaly correlation is slightly better with AI systems than whatever. We're talking about hours to 2-day type forecasts and features that develop a particular location may never have seen before, very intense local features. And I think no one has really tried to do that. On the other hand, Ryan Sobash has been working with the ensembles, and there's so much output from the ensembles, real-time ensembles, that he's finding use in AI in going through and being able to interpret all the ensemble members to come up with probabilities of severe weather, that kind of guidance, and that seems to be working. And so I think that's sort of where the emphasis might be with AI for this kind of weather.
Just one note, Rich wasn't the only one watching virtually. Lou Wicker tells me there were about 20 people at the National Weather Center down at Norman, Oklahoma, watching, and I think they liked your seminar. Lou didn't say.
And with that, let's thank Morris one last time.